Alright, hello. So this is problem 5 on the Unit 2 exemplars. My previous video got cut short, so I just left all the writing up there. So the problem states that using the wavelengths given in the diagram and knowing that the ionization energy of lithium in its ground state is 5.39 electron volts, what are the ionization energies of the 2p and 3s states of lithium? So starting with the 2p, the diagram gives us a wavelength of 670.8 nanometers. Plugging that into our known equation of E equals hc over lambda, we get 1.85. We want to find the difference between the 5.39 ground state value and that value, which means that we get a 3.54 electron volt ionization energy at the 2p state. So now for the 3s, we do the same thing. 3s can't go to the 2s directly, so we have to make a stop at the 2p. So we have to do a little bit of addition here with our equation. The 3s to 2p wavelength is 812.7. Doing that math gives us this value, and we want to find the difference again to get the ionization energy. So we have a 2.02 electron volt ionization energy in lithium's 3s state. The next part of the problem is using the wavelengths given in the same diagram, compute the energy difference between the 3D and 4D states in lithium, compare those values with the corresponding n equals 4 and n equals 3 energy difference in hydrogen. Why is this agreement so good considering the different values of Z between hydrogen and lithium? So starting with lithium, we do 3D, can't go straight to 2S, so we have to do more addition. The 3D to 2P wavelength is 610.4. We already know the 2p to 2s. Doing that math, we get 3.88, and the difference between that and the ground state level is 1.51 electron volts, which is the ionization energy of lithium at the 3D state. For the 40, we have the same thing, can't go directly, so make a pit stop at 2p. Our 40 to 2p wavelength is 460.3 nanometers from the diagram. Doing that math, we get a difference of 0.85 electron volts, which is the ionization energy of lithium in the 40 state. Now comparing these to our hydrogen-like atom, the hydrogen-like atom model gives us a general equation of e to the n equals z squared over n squared times E naught, where E naught is negative 13.6 electron volts, and the Z value for hydrogen is 1. So plugging that in at n equals 3, we get a value of negative 1.51 EV, which is the same value here as our 3D ionization energy of the lithium atom. Using the hydrogen-like model for n equals 4, we get 0.85 electron volts, which again matches up really nicely. These values are pretty much the same. The agreement is so good because the valence electrons act the same way, and they do that because they have the same number of valence electrons in their atoms. The final part of this problem, we have that the ground state of singly ionized lithium with a Z of equal to 3 is 1s2. Use the hydrogen-like model to predict the energies of the 1s1, 2p1, and 1s1, 3d1 excited states in singly ionized lithium. Compare your predictions with the measured energies, which are respectively negative 13.4 and negative 6 EV. Why does the hydrogen-like model work so well here? So my prediction based off of the second part of the problem is that these energies will be extremely close. With lithium, plugging that into at the 3D, plugging that into our generalized equation, we get negative 13.6 EV compared to a negative 13.4. That's very close, which is what I predicted. And then with the 2p state now, with an n equals 2, we get negative 6.04 EV, and that is a 0.04 EV difference, which is even closer than before. So my theory prediction held true. The hydrogen-like model works so well because both elements are in the same column of the table of elements, so they have the same number of valence electrons, which will act highly similarly when doing ionization and finding their ionization energies. So that is all. Thank you.